Okay, so let's get started today. First, quick reminder that first homework assignment is due Thursday at 11:59 p.m. and you should submit it via Blackboard. And the second homework assignment is already posted. In fact, all of the homework assignments for the semester have already been posted. If you go to the lecture notes, you can see all the stuff associated with homework 1, and then today I've posted, or you can, Thursday you can start into homework 2, but if you want, you can always start early as well. Also, there's a lot of slides for today's lecture on the data definition language, and I'm not going to go through all those slides because a lot of them are just syntax things that you can review on your own. So definitely make sure that you go through the slides after class today because you're responsible for the material on those slides. Also, when you're writing queries, you will need the material on the slides, but sometimes it's just very mechanical kinds of stuff that you can just look at the slide and you'll know how to do it. And so I don't feel like I should repeat obvious stuff. So it'll be stuff that I think needs to be emphasized that I'll be going over. We're actually going to start with subqueries, which we didn't finish last time, and we'll finish today first before we get into SQL's data definition language. So subqueries, if you remember, are ones that contain one or more nested select statements. And sometimes you can replace them with joins, sometimes you can't. And if you can replace them with a join, it's up to you whether you use a join or whether you use subqueries. Sometimes people find that using subqueries make writing a query more manageable for them. So here's an example where we want to list the staff who work in the branch at 163 Main Street. And like I said last time, if you knew that Main Street was the branch with the code B003, you could simply say where branch number equals B003, but the chances are you don't. And so you need to locate the branch code associated with 163 Main Street. And the way you can do that is write a subquery that's nested in your main query. So here we select the branch number from branch where the street equals 163 Main Street. The nested subqueries get evaluated from inside out, so from the most nested to least nested. So this one I've circled in blue would get evaluated first. It would evaluate to, say, B003. Then we would execute the outer query and select the staff whose branch number is equal to B003. So that's a very simple example of a subquery. And that's what the resolution looks like. So the first nested query was replaced with B003. And like I said, this is an example where you could replace the subquery with a join. So you could just have easily said that I want all staff such that the staff's branch number matches a branch number in branch and the street in that branch number is equal to 163 Main Street. Okay, and like I said, in the homework, feel free to use either a join or a subquery. On a test, feel the same way, whichever way works best for you. And then there's 3 types of subqueries. The only type we got to last time was the scalar subquery, which is what this is. This is a scalar subquery is one where the subquery resolves to a single value, like B003. Sometimes that subquery is going to resolve to a single value using an aggregate operation. So here we were listing all staff whose salary was greater than the average staff salary, and in order to do that, we needed to first know what the average salary is, so we had to twice write this subquery which calculated the average salary, and then we could say where salary is greater than the average, and here, this one, the average, again, replaces this subquery, so we end up with, for example, if this average is 17,000, we end up with a query that resolves to the one you see there, where 17,000 has, in each case, been the result of evaluating the subquery. Okay. And we also talked about SQL variables, which only work with the MySQL command line interpreter. So you put an @ sign in front of them. That's one thing. And then the, if you do a colon equal to do the assignment, and then you can just use the scalar variable in your queries and not have to repeat the subquery multiple times. It shouldn't affect the efficiency of the query so much as it's just for you easier to read if you do it this way. So scalar subqueries were the first type. A second type of subquery is a so-called row subquery. The book kind of skated over row subqueries. It said that they returned a single row with multiple columns, but in reality, row subqueries actually can return multiple rows. And the only time you really use a row subquery is when you're using an exists predicate. So this is the first time you're seeing an exists predicate in the class. And here's an example of how it works. Let's say we want to find all staff who work in a London branch office. Then I could say select staff, so this is the staff information, from staff where, and then say there exists, we'll get back to it. So we do the subquery first. So we select all rows from branch where the staff is linked to some branch number and the city is equal to London. So basically for each staff member, what this query does is for each staff member, so if we have, say, these 3 lines for staff, what it's going to do, it's like a for each statement. For each line in the staff, it's going to see whether that staff person can link into a branch, which it should because this branch number is a foreign key, and the city of that branch is equal to London. If that returns at least one tuple, then this exists clause is true. So basically the exists clause says, it's like saying, is the set non-empty? That's the question. Is the set non-empty? If the set is non-empty, then the condition is true. Yes, these are, actually this one I need to post, but this one I will be posting. Okay, now, I think this is a really hard way to write this query. The book gave this as an example of a row query. So I think this is a fairly bad way to write the query, not particularly intuitive. Can someone suggest an easier form for this query? So we want to find all staff who work in a London branch office. So think about this for a second. So we want to find all staff who work in a London branch office. Okay, I claim that there's a simpler way to write that query. So I'll start it out. Select, and we'll say s dot staff number, and just for brevity, I'll say s dot first name and last name. Now, can someone finish this for me? Yes. Yes, so very good. So what Camille is saying is we can select from, say, staff S, branch B, where S dot branch number equals B dot branch number, and B dot city equals London. That query is a whole lot simpler, right? In my opinion. Same result. Okay, and some people view this as a drawback of SQL, that you can get the same result in multiple ways, but other people think it's an advantage because people think differently. You can draw your own opinions. So questions about that? Yes.
Is there a scenario where the row subquery is the only means of getting the solution you want?
Haven't thought about that actually, because I don't use the exists subquery. I would say that the chances are good that that is true, but off the top of my head, I can't give you an example. Okay. Pardon? Yes. So remember I said that this is the join, right? The question is, don't we have to join the two tables? And that joins the two tables. Remember, you don't have to use the sugar, syntactic sugar. So I could have said also, so another way to say this would be to say select blah, blah, blah from something like, say, staff S natural join branch B where B dot city equals London. That makes it clear what's going on. So that'd be another way that you could write it. So 3 different ways. You can, there's still more. Other questions? Okay. Then the 5th type of subquery is a so-called table, sorry, 3rd type of query is the so-called table subquery. And it returns in effect, it returns a set, and there's only one column allowed for each row. So as an example, let's say that I want to list the properties that are handled by the staff who work in the branch at 163 Main Street. So one way I could do that is I could select, and this is all property information right here, so select various property information from property for rent, where, and now the staff has to be located at the branch, which is at 163 Main Street. So I'm saying where staff number in, and now you can see I have two subqueries. This is a nested subquery within this subquery, which is within that subquery. So this one gets evaluated first, then this one, then this one. So the first one, this one is actually a scalar subquery. It returns, say, B003. Then the second one is a table subquery. And it's going to return a list of staff that are in branch B003. So it might return a table that looks like this: S001, S010, S103, maybe S050. So it's returning a table that has a single column, and now we're saying that we're selecting from property from rent, and in the property for rent relation there is a staff number attribute, and we're saying for each tuple in property for rent, if its staff number value matches one of the values there, then I want to include it in my result. Okay, and as an exercise, I will leave it to you, but again, it's actually quite possible to write this using a join. There's no reason you have to use subqueries here. You could write the same query using joins. Okay, so just some rules for subqueries. The big ones are that, with the exception of row queries, which you rarely use, the select list for a subquery typically only contains a single column. So for a scalar subquery, that's the value that's getting returned. For a table subquery, that's returning the column values for that one particular attribute that you want to be in the set. And the second big one is that when you're using your subqueries, they have to be on the right-hand side. Whoops, I misspelled from. You can't write the query like that where the subquery is on the left-hand side of the inequality comparison. The subquery has to be always on the right-hand side. That's just an SQL rule. So this would be illegal. So those are the two big things to remember when you write subqueries. Okay. So here's the last one where we're going to give you. So what I want you to actually do is take maybe 3 or 4 minutes and try to create the query for this using subqueries. I know you can do it using joins, but see if you can construct a query that would give you all the guests currently staying at the Grosvenor Hotel and use subqueries. And you can talk to your neighbor. That is fine. You will have to use, at least at one point, the current date function. Okay, so you'll be current date gives you the current date. Actually give you 5 minutes till 2:34 to think about that, cogitate. If you have a question, feel free to raise your hand. If you get it in less time than that, then you might want to think of the join way of doing it. Sure that we are recording. Yep. So this is what my solution looks like. So you see that I used 2 nested subqueries. The first one was to find the hotel number that was associated with the Grosvenor Hotel. And then the second one right here, this is a table subquery. And what it is doing, can someone tell me what it is doing?
It's selecting all the guest numbers
Mm-hmm.
from booking where they're currently staying at the Grosvenor Hotel.
Right, so select all guests who are currently staying at the Grosvenor Hotel. That's kind of what you have to think about is, okay, what do I need? Well, I would kind of like to have a list of the guests who are currently staying at the Grosvenor Hotel. So that's what I am getting there. And to do that, I can get that by saying I want all bookings where the current date is between the date from and the date to. So that gives me all guests staying at all my chains or at all my hotels. And then I further whittle it down to those staying at the Grosvenor Hotel. And finally, I need to print all the guest information. So while this query right here gives me a set of guest numbers, it doesn't give me the guest information. That has to come from the guest relation. So I basically say print all the information about a guest where that guest number is in the set that gets returned by this particular table query. Okay, does that make sense? Yes, Suresh.
Is that star from guest equivalent to all guest number, guest name, and guest address?
Correct. So the select star says to print all attributes from the guest relation. So this will, yes.
When we started doing this, you wrote that current date was.
I know, I put a,
Is that like a shorthand?
that's a shorthand. You don't need the break parentheses. So parentheses are not necessary, apparently. Yes.
On the homework, there's a question kind of like this about like who's staying where. But
Mm-hmm.
is that the syntax you want us to use for current date, or how do you want us to decide what the date is?
Use current date. Yep, that's the way to do it.
Is there any advantage using subqueries instead of join?
Nope. The question was, is there any advantage to using subqueries rather than joins? And none that. It may be somewhat more efficient one way or the other for the query optimizer, but you shouldn't worry about that. Basically, it's whatever works best for you, whatever makes more sense. Because in fact, there's the same query that involves a join.
Can we write select star next there?
Yes, so you could have, the question was right here. This time I did not write select star. I actually wrote them all out, but you could have written select star right there. In fact, it would have been probably better. Okay, so I say you a lot of times can get it using a join. Now there was one query we had where you absolutely could not get it with a join. So right here where I wanted to select staff whose average salary was greater than, or whose salary was greater than the average salary, there was no way to get that via a join because you were using a scalar. But when you're using these table queries, table subqueries, my guess, I've never looked into it and tried to do any kind of proof, but my conjecture would be that any problem that you can solve using a table subquery probably can also be solved using a join. That would be my conjecture. Any other questions about subqueries? Like I say, I don't think there's a particular advantage to either way. It's just what appeals to your style. Whichever way you think is a fine way to do it. Okay. So that basically concludes our discussion of the SQL data manipulation language, and probably starting late Thursday, or if not Thursday, then Tuesday, we will talk about the relational algebra and relational calculus, which is the theoretical underpinning for the data manipulation language for SQL. We've already talked about the theoretical underpinnings for the data definition language for SQL. That was in Chapter 4 when we talked about the relational model. And the main things that you do with SQL data definition language directives. Remember, the data definition language is essentially about creating the database and specifying its structure. So that involves fundamentally creating and altering tables. And when I say alter, I don't mean insert a tuple or delete a tuple. I mean by alter, add a column name or delete a column or change an integrity constraint or change what happens when you delete a primary key, change the behavior of the database, those kind of things. And the third thing is defining and maintaining views. So the big three: create and alter tables, specify integrity constraints, define and maintain views. And this is what I meant by, I'm not going to go into huge detail over all the slides because a lot of it's pretty boring, but there are some interesting things that we will highlight. First of all, SQL has some built-in data types for date and time because that's pretty important into the business world and also even in the science world, being able to timestamp stuff. So there's some built-in date and time. There's also, they make a distinction between exact numeric types versus approximate numeric types. In programming languages like C and Java and Python, they all use approximate numeric types for their floating point numbers. But if you're in the business world, especially the business world, you often want to deal with precise numbers. You don't want 8.2199999, you want 8.22. So they give you the ability, there's 4 ways to actually specify precise things, and 2 of these, numeric and decimal, involve floating point numbers and allow you to specify precise, that they be stored precisely. Okay. Another thing, there is for Boolean a third truth value for Boolean called unknown, which you represent as null. Remember, null in general represents an unknown value, so there is actually a third truth value for Boolean. For character data, remember I said that you can either specify a fixed length field, which is char, or you can specify a varying length field, which is a varchar. And then there is a whole set of limitations on the sizes that you can use for the different char data types, and you can look them all up. As you can see here, char and varchar are limited to 255 character strings. Text is used to store longer strings up to 65K of characters, and you can get even bigger strings if you go and look at the SQL documentation. Okay, and then, as I said, you can get precise floating point numbers. You can, for example, say that a salary is decimal 7, 2, which means that there are 7 total numbers. So this is saying that the salary can store any number up to 99,999 and 99 cents. So 7 total digits, 2 after the decimal point, and these are stored as strings in the database, not as numbers, because someone tell me why they would have to be stored as strings rather than numbers in the database?
Well, you're trying to preserve precision.
Right, and
I don't know necessarily why you would have to store it as strings. Like, I think you could also probably use multiple integers. I don't know.
okay, yeah, I suppose you maybe could do it with integers, but the bottom line is there's certain floating point numbers you can't
I know you can
approximate using
I know you can
binary
approximate.
arithmetic. So you basically, the reason is because programming languages in general don't have a way to store precise floating point numbers. They can only do it approximately. So it turns out that usually strings are the most compact way that you can store it. Now, there's some older languages like COBOL that used to have the notion of packed decimal, where they kind of did what you suggested, David. They knew that there was 8 bits to a word, and they knew that you could represent any integer with at most 4 bits. So packed decimal meant you would pack 2 integers into the same byte using 4 bits for each integer. So that's kind of, I think, along the lines of what you were suggesting. That's not how it's done with SQL. This packed decimal is twice as storage efficient because it only uses 4 bits per number, whereas the strings use 8. Okay, so that's just the thing I wanted to point out there, and I'll let you read the other things. So dates, there are 3 types of data types for date and time. I rarely use timestamp, but you could imagine, like on a homework assignment, wanting a timestamp for when you submitted it, or when someone finishes a race, or when a package arrives. If you're Federal Express and you're processing packages through your plant or your warehouse, you could certainly imagine wanting to put timestamps in your database for when it arrives and when it departs. And the date's very picky. You have to go exactly supposed to be in that format. And same thing with time. It's supposed to be in that format there. There's also handy functions for manipulating dates, because often you want to be able to subtract 2 dates. Like if I have date from and date to in my booking, then a reasonable question is, how many days is the customer staying at our hotel? And it would be nice if you could just somehow subtract date from date to. And that could be big because, let's say you're at the end of a year, so let's say it's 2012-28 to 2014-016, you can see that it might be very handy to have some kind of arithmetic operations on your dates that nicely handle stuff like that, where you cross month or year boundaries, and you do. Date add, date sub, date diff. So date diff is the function you'd want here to return the number of days between two dates. So again, not going to go through these in detail. When you start working on the homework assignment, you can kind of go back to these slides, look at them, find the functions you need. But it is nice to know that there are handy date functions that will manipulate the date data types. Okay, I'm not really going to talk about interval, let you read about that. So that's pretty much the interesting things about the data types provided by SQL. Everything else pretty much conforms to the data types you use in normal programming languages. So what you know about them carries over into SQL. Then as far as integrity constraints, you've seen these already. We had 4 integrity constraints we introduced in Chapter 4. Does anyone know what the 5th one is here? What's the one we didn't talk about in Chapter 4? Domain constraints. Very good. So we talked about required data. We talked about entity integrity, which is that you can't, every primary key has to be both unique and non-null. Referential integrity, which is that foreign keys refer to a valid existing row in the parent relation or are null. And general constraints that are organization specific, such as no staff member handling more than, in this case, 100 properties. And SQL has commands we'll see in a moment for defining these types of constraints. Okay, so if for required data, you have to explicit by default, it is optional. So if you want to make it mandatory to provide a value, you have to say not null. So this position is the name of the attribute. It is a varchar with up to 10 characters, and we're saying not null. Then for domain constraints, sometimes we want to limit the domain of values, further restrict it beyond, say, just saying that sex is a char. So here, that doesn't restrict it enough. We actually want to restrict it to either a capital M or a capital F. And there is in SQL, but not MySQL. MySQL will syntax check it, but not actually perform the check. The SQL standard just will. But this is saying check this condition, and then this is an ordinary SQL query. So sex in M or F. So this right here can be pretty much any valid where predicate. So where you would use a where predicate in a query, the syntax for check follows the syntax for a where predicate. Yes?
What if you're trying to restrict the domain in, I guess, the opposite manner, in that it can be anything except for something? So like if it's a username, it can be anything except like vulgarities.
Mm-hmm. So I am guessing in that case you could say username not in, and then list out your, yep, so you just use not. And I'm guessing that there's also, we'd have to, yeah, so same thing. You'd take it and you'd use not. So you take your query and then you would just invert it using not, I think. Other questions? Okay. However, for passwords, you probably don't want to employ that restriction. And just like in regular languages, you have enumerated types so that you can have a convenient, you could say, for example, in Java, enumerate days of week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. You can do the same thing in SQL. You can create a domain and then use that as essentially that enumerated type in your subsequent declarations. So here we're declaring a domain called sex type. Probably a better word the book could use would be gender type, but that's what they use. And now you can use that when you're declaring a column attribute. Now, it's more powerful than using an enumerated type. You'll see that in a moment because I could, for example, check that the value is in any branch number that is in the branch table. So I don't have to, here I actually enumerated all possible values, but sometimes you will pull all possible values from a relation using a predicate. So here we go. We're creating branch number as a domain, and it can be any value that is associated with an existing branch number in branch. So there, I didn't have to physically enumerate every valid branch number. Instead, I simply said it's any, I created a set by selecting branch number from branch. I'm saying any value in that set is a legitimate branch number. And what's nice is that as the branch numbers are added, if we add a new branch to our organization, then the domain automatically has this value added to it. So it's not static like you have with physically enumerated ones. So that was domain constraints. Then with entity integrity, basically there are two ways to tell SQL that the values in a column are unique. One is by declaring an attribute or set of attributes to be a primary key, and that's a promise that they will be unique. But you may also have, remember you could have candidate keys, which are keys which have also uniquely identify each tuple in the relation, but they were not selected as the primary key. But you still might specify, as an example, that a telephone number is unique. Okay, they don't duplicate telephone numbers. So that is a way of saying that it is unique. And if you do declare it unique, because of entity integrity, you also have to say not null. So you would also have to include not null there. Okay, then with referential integrity, that's where you're declaring your foreign keys. So you specifically tell it two pieces of information. You tell it what is the name of the column that's the foreign key and what branch or what relation it is referencing. And that's saying that anytime you use a branch number in this relation here, you're guaranteeing that it matches a branch number in branch. So here you didn't have to create a branch number domain. You just say it references branch, and that guarantees that SQL will check to make sure that when you insert a branch number into whatever relation this declaration is being dropped, it will match some branch number in branch. And then remember we said that when you insert or delete a primary key, that's going to have ramifications for the foreign key. So if I insert or update a branch number in the branch table, then I need to know what happens with the foreign keys. And when you define a foreign key, you're allowed to provide 4 options for what happens. So cascade means that when you delete the row from branch, you'll delete any matching rows from, say, staff. So if I shut down my branch at 163 Main Street, I presume I'm firing all my staff. That's cascade. Set null says that I will keep all those staff tuples, but I will set their branch to null, meaning they're temporarily unassigned. Set default says that I will reset the foreign key to a default value. So maybe I have a specific branch which is headquarters, and I decide that if a staff member is unassigned, they're temporarily assigned to headquarters. So I would use set default, and then it would be assigned the default value for the foreign key. And the fourth thing is no action. So when I define my foreign key, I can in staff, I can actually specify no action, and that would stop the parent from being deleted. You couldn't delete the branch because the staff, until you delete it first, all the staff tuples. So those are the 4 options that you get, and you specify them when you specify the foreign key. So you specify it with the foreign key, not with the primary key. So there's a couple examples. Foreign key, staff number, references staff, on delete, set null. So perhaps this is for a property. This might be for a property, and perhaps the staff member resigned temporarily. We're saying the property is not being handled by anyone. Okay, here we are having a foreign key for an owner number, and we're saying if the private is referencing private owner, so maybe this is a contract, and if the owner number is changed in private owner, then that change would be cascaded down and changed in our contract as well. And notice you specify things for delete and update. So you might have different conditions for update and delete. Typically for update, it's going to be cascade because you want to see any updates that were made to the parent relation. So usually for update, it's cascade. Delete, though, is much more flexible. You could make a case often for any of the 4 actions. Questions about that? Okay. And then the general constraints, you can create in SQL a constraint by using the constraint keyword and then check. And in this case, you are specifying, again, any valid where predicate works here. Hey, and I think earlier, what's your name again? Mitchell? Mitchell, I think earlier you asked, is there ever a time when you could, well, I think your question was something along the line of, can you always replace an exist query with some other query? And at the time I hedged because I was thinking I knew of a query where I didn't think you could easily replace it, and this is the one. I think here you pretty much have to use a not exist query. So what we're trying to do is prevent any staff member from having more than 100 properties. So actually, turns out we have to first find all staff members who manage more than 100 properties, and then we want to say that doesn't exist. We want to say that's the empty set. And I actually don't know of any other way really of easily expressing this query. It seems like this is, in fact, the easiest way to express it. Okay. So so we just went through, okay? So first one was required data, okay? Second one, we talked about domain constraints, then entity integrity, which is primary keys, referential integrity, which is foreign keys, and general constraints. Now, MySQL, it's public domain, and it doesn't support all of this stuff. And the reason you still need to know it is because this is in the SQL standard. So create domain is not supported in SQL. And if you try to use it, you'll get a syntax error. It's not even supported. Check and foreign key references are parsed but not enforced, which is annoying. So it'll check it for syntactic correctness but will not actually enforce them. So it's not basically enforcing domain constraints, referential integrity, or general constraints. It's only really enforcing required data and entity integrity. But that's what you get when you don't pay for something. Okay, it is public source. They do, MySQL does support a physical enumeration, so it has a limited form of domain constraints. Yes, Suresh?
What about the comments by the client? It's a candidate key, but some can be null because they always done the comment.
Not if it's a candidate key. So by definition, a candidate key says that it uniquely identifies each tuple in the relation. So by definition, a candidate key cannot have a null value.
So how do you classify comments as?
In a viewing relation?
Yeah.
So the comments, they're not necessarily unique. The same client might say, this was wonderful. Nothing to stop them from just saying something vacuous like that, right? So there's actually, technically, they're not necessarily unique, okay? Or one word, awesome, maybe. Other questions? Okay. So that took care of the syntax for integrity constraints. So remember, let's go all the way back to the beginning. We said there were three things: create and alter tables, specify integrity constraints. So we kind of skipped ahead and did all the stuff with integrity constraints. Now we're circling back and we're talking about creating and altering tables. Whoops. Okay, and again, this is something where I'm going to let you do a lot of looking at my slides because it can be pretty tedious. The big things that we're going to look at are creating tables, altering tables, dropping tables. Makes sense? Creating and dropping views, and many database management systems also give you a way to create or drop an index on a column. It's not in the SQL standard, but is pretty much something that every database management system worth its salt is going to allow you to do. And you can see there the syntax for create table. Feel free to look at it on your own. I don't think that it helps if you're trying to write one, but doesn't help for me to go through it right now. Obviously, create table creates a table. You specify all the column attributes. You can specify default values for columns, primary keys, and let's just skip ahead to an example. So here we're creating the table for property for rent. I'm assuming this is the full SQL standard, so P number, P rooms, P rent, I defined them all as domains on the previous slide. And by the way, in my notes, when I underline something, that's the primary key. So when you see me underline something, I mean primary key. So here I'm declaring property number to be a P number, not null. And then down here, I'm defining it to be the primary key. And you can see for rooms, I'm giving a default value of 4, so I'm saying that it has to be not null, but I'm also giving it a default value, so when you do insert into a table, you don't have to provide a value for rooms, even though it's a mandatory attribute, because if you don't provide its value, SQL will fill in the value 4 for it. Same thing for rent. It will automatically receive the value 600 if you do not specify another value. Then you can see that for staff number, I had earlier defined the constraint staff not handling too much. Actually, this one I'm defining it here. So this, remember back here, way back, not so far back. There we go. There's that constraint, and here I went ... but the rest of the constraint would go right there. Okay, then here we have foreign key, staff number, references staff, and the options. So on delete, we're going to set the staff to null, on update will cascade, and then again I just ... it for the rest of whatever information I wanted to put in there for property for rent. But that gives you the basic idea for how you go about creating a new table and specifying the information about it and the different kinds of constraints. So questions about that? Okay, then I'm going to let you look at the slides on your own because this is very straightforward. So I'm not going to go through it. I'll just let you. It has fine examples. Going to skip ahead to indices. So indexes, a strategic use of indexes can make it much easier for a query optimizer to optimize a query. Just like a table of contents in a book makes it much easier for you to find the right page number. Same thing with an index. So you can index specific columns. Sometimes you can provide indexes on combinations of columns, because remember, primary keys are sometimes multiple columns, in which case you'd want to potentially create an index on multiple columns. And there are, in effect, two things you can do to organize a relation. The first is that typically you can choose one field or sometimes multiple fields on which to physically sort the relation. So for example, you might sort the relation by last name or by social security number. You don't always sort it by the primary key because you actually look at, we'll get to this when we talk about physical design in Chapter 18, but sometimes there are queries that are frequently executed, like find someone's name. That might be executed much more frequently for some reason than find their social security number. So it's possible you would actually physically sort it on a non-primary key, although that'd be a little unusual. And then the second thing you can do is you can put indices on any column, and that can help the query optimizer to find things. So here I'm finding a staff whose last name is White, and perhaps I have physically sorted the staff relation by staff number, but if I didn't provide an index for last name, then the only way I could find all staff members with a last name of White would be to physically search the entire relation, right? I'd have to go through every tuple in the relation. But if I had an index, then I could simply find all the entries associated with White in the index, and it would point to the right places on the database or on the physical files to find them. And also sometimes you can satisfy a query without even going to the database if you have the right index. So let's say I had an index on salary and I asked for the average salary. A good query optimizer wouldn't even go to the database to calculate the average salary. It would just go to the index, knowing that the index had every salary for each staff person in the organization. It would simply add up all the salaries in the index and divide them by the number of entries in the index. So a clever query optimizer can sometimes solve an aggregate query just using indices and will not even have to go to the underlying database, to the stored base relations. So that's something that we'll look at for a bit when we get to chapter 18. It's kind of black art, meaning it takes a lot of experience often to select the right fields to index, and also you often tune the database once it's operating. You can juggle the indices to see if you can't fine-tune the performance. The question I always get is, why not put an index on every single column in a relation? Can anyone answer that question? Seems like if indices are such a great idea, why not just index every single column in my relation? Pardon? Some columns, right. So that's one good answer. So one good answer is some columns are rarely used in a query, at least in the where predicate. And so they, like first name is rarely going to appear in a where predicate. Sometimes, but it's rare. So perhaps you're just wasting space.
Would that not be equivalent to looking at each row again if we indexes all the columns?
So, okay, so Suresh said, kind of wouldn't it be back to looking at every row, which in some sense is true. If you index every single row, you've basically duplicated all the information in the database a second time. You really have two databases. Okay, so that's a lot of space down the tubes. Okay, third reason is you could overwhelm the query optimizer. The query optimizer, you give it too many options for optimizing a query, and now it's going to think for a long, long time about the best way to do it, because it's going to keep trying different indices or different combinations of indices. It makes estimates of how many tuples it will have to retrieve using every combination of indices. Well, if you have 5 indices, I believe there are 2 to the 5th or 32 different ways you could combine them. So it has to consider potentially 32 strategies. Now if you have 10 columns and 10 indices, that's 2 to the 10th or 1024. Notice we're getting an exponential blow up in the number of strategies that your query optimizer might have to consider. That's another reason you don't index all of your columns. Okay. There are other reasons, but those are 3 good ones. Okay, we're not going to worry about that. Okay, I'll just give you a quick introduction to views here. We will finish up with them on Thursday. So remember from chapter 4 when we talked about relations, we said that you can define virtual relations which aren't necessarily existing in the database, but they're produced upon request at the time of request. And I said Also, you might cache them. So a common example of a view is one that gives a report that reflects aggregate values. In this case, I have a report showing the number of properties managed by each staff member. Another reason we'll see for creating views is to simplify a query that would otherwise be pretty complicated to express by itself. So remember, with the subqueries, a subquery could return a table. Oftentimes the subquery can be pretty complicated, and if you try to put several nested subqueries in the same query, it can get pretty nasty looking. So sometimes what you will do is define a view to hold an intermediate result, like a subquery result, and then you will do a, you'll retrieve tuples from that view in your final query. So we had scalar variables for storing scalar results from subqueries. Views can be considered a comparable way to store a table result. Okay, and say a view is defined as a query on one or more base relations, and there's two ways to support them. One is to automatically translate the query into operations on the underlying base relation. That's called view resolution. The other is to cache the results stored as a temporary table, and that's called view materialization, but it's really just caching. And there's two types of views. There's horizontal views, which only show a subset of rows. So you see all the columns, but only a subset of the rows. For example, the manager of branch 3 only needs to see the employee information associated with staff at branch 3. So we might give that manager specifically a view called manager 3 staff that shows the employees in branch 3. And associated with both views and relations are access privileges. We're not going to cover that in this course, but that's an important part of database security, is you can give different people different access privileges. So you might, if I'm the manager of branch 3, I might be the, say, one of only a handful of employees given access privileges for manager 3 staff. Okay, and some other people might be given read access, but perhaps not write access. So that's what I mean by different access permissions. And then a vertical view is you see all the tuples, but you only see a subset of the columns. So that's called a vertical, because it's like a vertical slice from the relation. So do I have a picture? No, I don't. So vertical views, it would be you might only see this column and maybe, say, this column. So that's a vertical slice. Whereas a horizontal view, you might see this part of it and this part of it, so you see a horizontal slice. So here, I'm giving a view of the staff relation where I've deleted the salary. So maybe someone in human resources needs access to the staff, but unless they're in the payroll department, we don't want them to see the employee's salary. Obviously, you might not want people getting jealous, stuff like that. Okay, and then the third type of view, so I had row views, horizontal, vertical, and the third type of view uses aggregate operations and draws data from multiple views. So here's one that gives me the count of properties managed by each staff member. So I create the view staff property count. These are going to be the three names of the three columns. And then this is called, we'll get to it next time, the defining query that defines the tuples that will appear in the view. And the defining query is written just like the queries that you've seen thus far in Chapter 6. So any query that was valid in Chapter 6 is valid here in Chapter 7 for creating a view. Yes, Suresh? Pardon? The indentation is the same too. Okay, just something that makes it look nice. Okay, so we'll pick it up from here on Thursday. Remember, homework is due Thursday night at 11:59 p.m.